Hello friends, welcome to the module number 4 in AI. Right. We have named it as unguided search methods. You have seen that AI is possible to be solved, the problems of AI are possible to be solved using a method called state space, where we can define these problem states in a state space. We have an initial state, we have a final state, we move around in state space, so on and so forth. In the previous modules, we have seen how can one define a state space, how can one define move, and so on and so forth. One important aspect of the process is moving from the initial state to the final state. And we have already seen that AI programs don't have, AI problems don't have the algorithms, AI solutions don't have the algorithms. So you just don't have a clear-cut method to begin from initial state to reach to the final state. You will have to search for final state, and that's precisely is the important part of this particular model. This is precisely what we are going to address in this module: how to search, how it is possible to search. There are basically two different types of search methods. In this particular module, we are going to see simplest of them, called unguided search methods. Unguided search methods means we don't use heuristics, but we use simple methods to solve search from the initial state. We begin from initial state and reach to the final state. So we again go back to our trivial problems that we have seen in the second module, and we are going to explore them a little further here, and we'll see how one can apply these search strategies. There are few strategies which are quite simple, as I said, but quite useful as well. You may be surprised, why should we talk about unguided search, as we have already seen that most of the AI problems require heuristics, and the unguided search methods don't use. The guided search methods actually use heuristics, where you can say that this move is better than the other, or some estimate about how good or bad a particular move is. So why we are talking about unguided search methods too? First, if you learn about unguided search methods, you can always improve them by providing heuristics. So the guided search methods are not something which is different than unguided. They are unguided search methods with the use of heuristics. So that whatever we study here is going to be useful there as well. And second, sometimes when you don't have heuristic, but the problem domain is small enough, you can go for unguided search methods as well. So unguided search methods are not all that useless kind of. They are quite useful. So we are going to discuss that. We have already seen AI is trying to solve difficult problems, and difficult means something that is hard for computer to solve, not humans. First step we have already seen, generating a state space. Building a state space is what we have seen in last two modules, but that's not enough. We need to have some strategy to move around in state space, and there are some characteristics of that strategy also. Let us see what that is. The maneuvering process itself is called search. For example, a maneuvering program in chess probably looks at 1,000,000 states during the chess playing session. So let us first of all try to talk about one of the simplest requirements. First requirement is that the solution path should not contain any cycles. Look at three examples given on the slide: 800, 350, 800. What does that mean? You power milk from 8-gallon jug to 5-gallon jug and power it back. Now this is a cycle. Now if there is a cycle in the solution path, you may not reach to a solution, because cycle may go on forever. You just power milk from here to here and here back, you won't get to a solution, but you won't come to an end as well. So that is one thing which we do not want. We do not want any cycles in the solution path. So that's the first requirement. In fact, you can easily see that the other requirement is we should be moving actually. The cycle, what does that mean, that you should have cycles, that you should be moving further? If there is a cycle, you are not moving further, you are circulating at the same place. And there are two other examples. You can see 800, 503, 053, 350, 800. Now this is something which you should try to avoid. You can see that in the third one also you have a cycle. Why we want to avoid cycle? Let me repeat, we do not want to continue further, we do not want to continue forever. If we would like to reach to a goal state, the most important thing is that we are moving, and if we are not moving, we will not be reaching there. Okay. and the state generated should not be generated again. That is what we mean by a cycle. And in fact, you should explore everything in a systematic way. Okay. And it is quite possible that you traverse some futile, useless states. You just try in that direction, could not solve the problem, come back and try some other direction. That is quite possible, and that happens in our manual case as well, and the program is probably doing that as well. So, we have seen some other examples earlier where we have clearly stated that this is the solution, and we say that the program is going to do it that way. But believe me, when you write the program may try futile paths and then probably embarking on the right path. Okay. This type of search where we do not have any help from heuristic, we do not have any domain knowledge, we do not have any information about which move is better compared to others, we call it unguided search. Okay. But in that, believe me, in fact, that is what we are going to see, that some typical types of moves are better than others, but we do not know that thing right now, and that is why we are using unguided search. Okay. We have already seen some domain knowledge. If you have that domain knowledge, where you can say which move is better than the other, is called heuristic. If you use heuristic, it becomes guided. If you do not use heuristics, unguided. Unguided search is used at two cases. There is not enough domain knowledge. We do not know. Okay. And when there is some guided search already applied, the problem domain becomes so small that you can not worry about. You do not need to worry about heuristic. You just try exploring all possible options and solve it. Okay. Now, let us talk about the first method. It is called generate and test. It is about picking up a random state and checking if it is a solution. Surprising? We are doing it, in fact. This is something which we do every day. For example, when I am coming for college, I am looking for my car keys. What should I do? I will just look at my pocket if it is there, and where I am hanging my keys, and if it is not there, I will look at my table drawer, and if it is not there, I will search for my daughter. Okay. She is fond of playing with my car keys. So, that is what I am doing. In fact, I am trying for a state. My pockets is one state, the place where I hang my keys is the other, my table drawer is the third. I am testing everything for solution. I will try exploring all possible cases until I get one. So, that is an example of generate and test. Anyway, there was one excellent expert system which was known as Dendrel, designed to use generate and test. What it does is pretty complex. It works like a geologist. So, it looks at the sample of earth and do something with it. It tries to figure out what it contains, okay, the kind of mantle and all that, what the content of that sample, okay, it tries to figure out. Okay. It takes two things as input. Spectrometer reading, and there is something called mass resonance spectrometer reading. Do not ask me further, I do not know. These two things are coming inside as an input to Dendrel, and what Dendrel does, it looks at the input and try to figure out the chemical compound structure. Looking at the results, the candidate structures are calculated and checked for a match. Okay. What are the possible candidates, and we will just look at them and check them with matches. They will just give you the Dendrel, the output of the Dendrel is small set of states which matches, and there are many candidate structures. In some cases it goes beyond million. So, it does a simple thing. It collects those big bunch of structures, match, and that matching is done by something else. In fact, testing, that is what testing is. First of all, it generates and then test. Testing is done by something called constraint satisfaction. Now, that is something else which we are not discussing right now, but constraint satisfaction also is pretty simple to understand. It just have some set of constraints. You know that in a chemical structure, something which is impossible is impossible. So, what you do is you just check for those impossibilities. So, if that exists, then this structure cannot be the real one. So, that is eliminated. These are all structures that are possible, but this structure is impossible in this case, so they are eliminated. So, those constraint satisfaction part uses the test. So, it is generating and testing them, and if it is found the match, it will store in the result database. Eventually, out of million possible cases, it just sorts out small range of small set of those chemical compounds, and which geologists can actually work on. So, that is a very good example of how one can use generate and test. In fact, the algorithm is pretty simple. Look at the slide. The algorithm, it begins with generate a random node from a state space, okay, my pocket for example, which I just did. Test if it's a solution. If the keys are there, I've got the solution, I quit. If it is not, I'll go to the first step. I try one more. The method is known, quite known, as I said. Finding keys is one example I've already given. This method is useless. If I have to search the key in an entire house, it is useless. But if I know that there are only few places where the solution can be found, it's pretty useful. And there is something called hierarchical generate and test. People at the forensic does something like this. They take the fingerprint of the criminal and they try to match with the fingerprints of the criminals in the database. Okay, so what they do is, in fact, they have hierarchical generate and test. So what do? They see if the fingerprint is curved or square or broken or things like that. So, and then it narrow it down and then try all possible cases, generate and test there. Something similar you probably have done if you are a science student and have tried to find out ions of given chemical compound. You try for class 1, then class 2, then class 3, then class 4. If it belongs to a specific class, you just run some testing measurements later. So, that is exactly what is happening here. So, the normal generate and test is applied only when the classification is done, but again for the classification also there is a generate and test. The first generate and test is to find out which class the sample belongs to, and then that generate and test is to figure out what subclass that the sample belongs to. So, this is the slide actually talks about one example. Fingerprint can be divided into curved and round and broken and all that. Then curved can have big curves and small curves, and round can have long rounds and small rounds, and so on and so forth. Okay. Now, let us see how the next method called breadth first search works. Okay. See, the first, now what we are doing is we are taking the same example, 853 gallon water jug. The root node is 800, our initial node. Now, what we do now is we apply all possible rules and generate all possible states which can be generated from 8 in the next level. So, the first one is 350, second one is 503. Okay. Now, what we are doing? We are pouring either the milk in 5 gallon jug or 3 gallon jug. Now, the second level of tree, 350 can be converted to 053. What does that mean? I am moving 3 gallons of milk from 8 gallon water jug into the 3 gallon water jug, and 323 moving 3 gallons of milk from 5 gallon jug into the 3 gallon jug. And the third one, 800, something which is already generated. We have already seen that this is something which we would like to avoid. It is a cycle. Okay, and that is why it is represented in little darker fashion. Okay, 503, there is one typical result is again 800, which again we will not explore further because it is a cycle. The one more possibility is 053, and why it is darkened? Because it is already explored. See the leftmost node which is already explored. Now, we are, when a node which is explored is already explored before, we will not explore it further for obvious reasons. And the third one is 530. Now, let us look at the next level. 350, which is already explored, is a parent basically of the same node, and 620 is the other one. 620 is also a child of 323, and once again we get 503, which is already explored before. So, we are not going to explore that further. Okay. And again 053 we have 233 and 350, which is again repeated. 530, one output is 350 and 503, both of them are already explored, so we will not look at them. The rest of the tree is just explored the same way, and what we get at the end, you can see that I get two different answers. One is 440 and the other one is 413. I have already told you that it is possible to have multiple final states, and here we can. Now, this is called breadth first search. I what I do is I pick up a root node, explore all children of it, next level explore all children of those children, and so on and so forth. That is the breadth first search. Dark nodes, here it shows that dark nodes are either repeated or something which are already explored. Okay. Let us try to understand the algorithm now. It starts with the start state as a root node. Repeated or goal is not explored further. Generate all children of the parent node, and obviously once it is done, it begins with the leftmost child, and all children of that and so on is explored, and it stops when there is no path ahead. What are the advantages of this method? This advantage, one of the biggest advantages of this method is you will always be able to get the shortest path through that node, and when that is very required, this is the search method to go for. And that actually, this search also has a pretty big disadvantage as well. What is the disadvantage? If you look from the angle of a programmer, this requires a lot of memory, and you don't really know how many nodes are going to be explored and what is the amount of memory that you need. Think of it. In this case, so the first level you have 1 node, second level you have 2, next level you have 4. In fact, every level you will be exploring 1 node for more than the total number of nodes that you have explored, even in the case where you have a binary tree. What if the branching factor, number of nodes from a given node, okay, an average number is higher? For example, chess, you have a branching factor of around 35. In that case, level number 1 is 1, level number 2 is 35, level number 3 is 35 into 35. Think of it. Every level increases number of nodes exponentially, and that is the problem with this approach. In most cases, you will not have the luxury of having that much amount of memory to store all those nodes there. Okay? So, that is the problem with this method. Now, let us look at the next method called depth first search or DFS. We will again start with 800. Now, we do not explore all the nodes, we only explore the leftmost. You can see 350 is the next one, 053 is the next one, 350, now that is the dead end. We have already come across 350, we will not explore this further, because if we continue to do that, we will end up in moving around in a cycle. So, now when there is a dead end, the last parent will explore its right child. So, it is right. Now, again we will try to explore the left child, which is 602, which again runs into trouble. 503 is already explored. So, what we do? We will explore the right child of the parent, that is 152, again a left, 143, so 143, then we have 440. Now, we have come to a solution. Now, this is called depth first search. We are going in depth, we are not exploring it, we just take a left route, left route, left route, left route, go and make sure that we get a solution. If dead end, we will try the right child and again left. Okay. The algorithm is simple. It begins with root node as a start node. If the node is a goal node, it quits, it explores the leftmost node, is a repeat node or dead end, we will try the right. Okay. Parent node is explored again to get its next child. If that parent cannot produce next child, the parent to parent is taken up. Okay. If the root node is reached and no further children to be explored, the search process ends there unsuccessfully. We cannot proceed further. We do not have any move to go forward. All nodes are explored, then there is no solution. Okay. Otherwise, we will go back to the second step. We will start all over again. What is the advantage? The advantage is this method does not demand the amount of memory that the BFS demands, and that is why this is adopted by many programming languages. One of the exceptional example of depth first search is used by Prolog, and there are other methods which uses depth first search. There is something called depth bound depth first search. Now, that is a little difficult to understand the first shot, but let me explain that in brief. Depth bound depth first search is there is some limit you decide. For example, you decide the limit of your search tree is 3. So, when you reach 3, it is dead end, you will not go further. So, you will have to try alternate. Okay. So, how it is done, you probably will understand by this figure. We begin with 800, we explore the leftmost 350 and left to it 053. Now, we assume that there is an end, we will not go further. So, we will take the right child of 350 and we get 1, again we reach to the final the level. So, we will not move further, we will take the right child of it, it is 800, it is repeated. Now, we take the right child of 8. Okay. So, in the beginning we will look at the 053, then 350's right child and then 800's right child. Okay. That is precisely what we are doing. So, 503 will take a left child, which is 800, next child 053, next child is 530. Okay. So, this is how depth bound depth first search is executed. Unlike depth first search, where you try going in the left until you are stuck, here we have an artificial limit. Here the artificial limit is pretty simple, 3. A level, if you look from the levels of tree, it is 2, but number of nodes it is 3. Okay. Then in the next cycle, what we do is, in fact, depth bound depth first search actually explores everything like the previous case, and then it starts looking for the solution like this. You can see that. Now, I do not need to explain every step. Now, you may be surprised why the first cycle is repeated again. You may not repeat, but if you are not repeating, what you are supposed to do is to remember the entire tree, and if there is a problem with memory, you cannot do that. So, you have to repeat that again. So, these are okay. The next one is called depth first iterative deepening. Now, here this is actually a subset of depth bound. In depth bound, you can assume some length, but this iterative deepening, it is only going to have 1 and not more. Okay. You probably think that it is a bit wasteful. If you have seen exactly what I have done in the previous case, depth bound, you explore the tree and then the next cycle you explore that tree again and then the next level, sounds wasteful, but it is basically not. When we study heuristics, we will study it further, but here let me tell you why it is not so. In fact, what you can do apply is additionally called branch and bound. Okay. So, you can always, once you explore that entire tree, you can apply heuristic and find out which moves are better compared to others. So, what you can do is you can, in the next cycle, you can explore them before others and see how expensive they are in the next case, and you can omit some of the branches. Okay. How it is done we will see later, but point is, though it looks expensive in the face of it, it is not so. Thus, first iterative deepening works like that. It starts with 1, okay, and then again start have 2 levels of tree, and then again start have the 3 levels of tree, and so on and so forth. And it is quite good, in fact, in the sense that is as optimum as BFS. If you get a solution, that solution is optimum. Not only that, the advantage, you do not need to have the amount of memory that you will have. You require in BFS. The only drawback of the system is that it takes more time and more memory, obviously, because it start all over again every time. But as I said, it is not necessarily a drawback, as it is going to help which nodes to be explored in the next class, next iteration. So, you can see how it works here. We start with 800, 350, 503. Okay. So, second cycle. You can see that it is being repeated yet again, but now for 2 levels, okay, now 3, okay. You can see that it is not difficult to understand how it operates. Okay, let us look at some comparison. DFS will find solution eventually if the search space is finite. Now try to understand what this means. In some cases the search space is not finite. If you try, for example, try to find a node with a value. For example, if you are exploring the search space containing all integers, you would like to find out an integer where the square of the integer and the cube of the integer is same, and you continue exploring that, you will never get an end to it. So, sometimes the search spaces are not finite. So, if it is the case, BF and DFS will not stop, but otherwise the later 2 search methods will eventually stop. You say that after 5 minutes you will have to stop and come back with best result, you can get that, and that is the reason why this depth first iterative deepening is used with chess. And there is something called virtual infinity. Virtual infinity is obviously not infinity, but then in real time you will not be able to handle that. So, that is all it is called virtual infinity. If you want the answer, the solution in minimum number of steps from the root node or the initial state, BFS is the best solution. I have already talked about this, the string X which are interested in checking and all this thing. If it does not hold, the process will not stop, and this is the example of the integer values that I was talking about. We must start with 4, 8 and 9, 27 and so on and so forth. We will never get two values which are equal. DFS, unlike BFS, do not guarantee optimal solution. You may traverse a very long path and get a solution. Is probably, if you have traversed on the other side, probably you will get it much earlier, but that is it. DFS may not get you an optimal solution. But then if you bound, for example, if you say that I will bound the DFS for 4 levels, and if you get answer, the difference between the optimal solution and the solution that you get is not more than 3. That is something which is an advantage of depth bound depth first search. Suppose if you were interested, and this is a real world example, suppose you want to write a password cracker, and what you are doing is you are just checking each password. If you try depth first search, you probably will not get, but if you try depth bound search, and if there is a password which is of 4 character or 5 character, and if you are just exploring, probably you will be able to crack it better, because it takes, otherwise it takes much more time. And obviously this clearly indicates that we need heuristic based searches. Okay, what we have already seen in this particular module, we have seen that we need an additional thing in solving an AI problem called search. We have an initial state, we have a final state, we need to move around in the state space, and that is what we call a search, okay, a method. And there are two types of methods, guided and unguided. Unguided search methods does not use heuristic, guided search methods use heuristics. In this particular module, we have looked at some of the unguided methods. We have looked at something called generate and test. We just assume that there is a solution and test if it is a solution. If it is not, we quit, they pick up something else and test, and so on and so forth. That is called generate and test. We have seen breadth first search, where we explore all nodes from a root node and try to see if the solution, again explore the next level and so on. So, we explore tree level by level and see if we get a solution. The problem with this method is that it is pretty expensive in terms of memory. One more method is to pick up depth first search. We only pick up one typical branch of the tree and explore it continuously, and come to a dead end, we take up the next branch and so on and so forth. We already seen one more method of binding it to typical length. It is called depth bound depth first search. We have already seen in a typical case of depth bound depth first search, where the depth is just 1, it is called depth first iterative deepening search. And we have seen that is quite good, though it sounds wasteful at the first sight, where you are exploring the tree again. It saves on memory, as well as if you are using heuristics with it, it is possible to choose better moves in the next cycle. So, it is not all that wasteful. Okay. So, these are all unguided methods. In the next module, we will be looking at guided methods, where we are going to see how heuristics can be applied to manage the search process in a little better way. Thank you.